right now, everybody we know has been born on this ball. Everybody we know everyone that's died has died on this ball. And basically all of our resources have come from there. There's been a little use of meteoritic iron in the distant past, but for the most part, we've gotten our resources from our home planet. And that's, I think, going to change in the near future. So let's do a little history here. If you've been following the news, there's been a lot of talk about asteroid mining. You know, it's a hot thing in certain circles, including venture capital circles, some of them. And you see these things, you know, like, let's see here, $1 trillion business, trillions to the world economy, and all that. Well, how realistic is that? Well, I hope to get into that a little bit today. So the first actual mention of asteroid mining was in 1898. So that's a century and 20 years ago now, or so. And this book was actually sort of a ripoff. The guy was the science correspondent for the Hearst publication, and Hearst told him when the War of the Worlds came out, which was a big, huge bestseller, he said, make a ripoff of it. So he did. And then he did a sequel where he used Edison's name, and back then the law was loose, so you could just use a famous person's name. You didn't have to worry about, well, did they object or agree or whatever. But this book had everything. It has alien abductions, it has the first mention of spacesuits, I believe, in a science fiction story, oxygen pills, and it had asteroid mining, actually being done by the Martians. And then if you follow science fiction at all, for a long time there's a lot of stories about asteroid mining, which really were kind of mappings, if you would, of terrestrial mining. They tended to be sort of grizzled guys who were out in the boondocks of the solar system and, you know, would have maybe very libertarian ideas, but also fairly bad hygiene, maybe, or something, and, you know. And there was a whole series of stories in this. Heinlein did it. The Lens stories had asteroid mining. Well, what about in reality? I've run numerical, you know, integrations of all the asteroids, asking the question, like, for example, the Dawn spacecraft is at Ceres right now. Would another asteroid come close by while Dawn is at Ceres that it could see it? Which basically means it needs to be about 6th or 7th magnitude. And so I did, you know, 50,000, 100,000 asteroids, something like that. No, is the answer. Every once in a while, some asteroids come close together that if you were on one, you could see the other with the naked eye. And if you're on, I mean, there's one that you can see on Earth every once in a while. I think it's Vesta. Every once in a while, Bamberger comes close enough to Mars that it's about 5th magnitude, so you can see it. Basically, no. The asteroid belt is very, very thin space. All right? So, in a way, this is more realistic. If you remember The Little Prince. Little tiny bodies that are probably not going to be round, but are sort of like little whirls in themselves. All right? So, there's people have talked about mining two things, and I'm not talking about science fiction, I'm talking about in reality. And the two things are stuff that's really valuable or stuff that's really useful. The stuff that's really valuable, I mean, people talk about all kinds of things, but really the most realistic thing is the platinum group metals. They're called platinum group metals because they have an affinity for each other, which means they're hard to separate in mining, and they're all fairly expensive, and so the miners typically at the first stage get them all together, so you'll get platinum. And the other thing is stuff that's useful, and the primary thing that's useful is water. You might have just regolith, just dirt, sand, whatever you want to call it. You might have there's hydrocarbons in some asteroids. I mean, we know a lot about asteroids because they fall as meteorites. Since we have pieces of lots of asteroids, we have the usual trouble that if you find a particular meteorite, you don't necessarily know which asteroid it is coming from. In fact, you generally don't. You generally don't have a clue. So you have you have these guys here, and you have the guys out there, and there's some connection between them. But we know some of them have got, you know, some of them are basically like tar sands. The Tagish Lake meteorite, which fell on frozen ice, and the guy had the presence of the guy living on the lake and the presence of mind to go out with plastic bags and scoop this stuff up and put it in this freezer so it's never been warmed up. Those things are basically like tar sands. You can probably make petroleum from them. So look at the platinum group metals. The latest prices I have on this stuff is about $50,000 a pound for platinum. there's palladium, rhodium, iridium, ruthenium, and there's osmium. They all tend to go together. They tend to be about more or less the price of platinum for, I think it's palladium, to a lot less for ruthenium. But just say it's the same as platinum, to just make it easy. And because you don't really know which mix you're going to get from any particular asteroid. Well, you can scale this fairly easily. SpaceX has a spacecraft called the Dragon, and actually the Red Dragon, which is supposed to be interplanetarily capable. In other words, you could send it out to somewhere, I mean, they're thinking Mars, but you could send it to an asteroid and then bring it back to Earth, okay? It has a cargo capacity of 3,310 kilograms. All right, so at $50,000 a pound, you just do the math, that's $165.5 million. Okay, well, the trouble is, the cheapest cost you can get to launch one of these things, I'm not talking about the cost of the Dragon, I'm just talking about the cost of the launch, is about $160 million. So you see you got a problem here making money, because I call this, the bars are on the surface and you just go pick them up. In other words, if there were just bars of platinum on the surface of an asteroid left there maybe by friendly aliens or something, and all you had to do is just go and pick them up, you probably couldn't make money doing that right now. Now, if you had an interplanetary infrastructure, if you were doing mining on other things and you had rockets going back and forth and all like that, so you're just, it's a marginal cost as opposed to a total cost, yeah, then probably you could make money from it. But if you have to pay the total cost, because the thing is, we think of nuggets. You know, you go to the Smithsonian Museum, you see these gorgeous nuggets, big nuggets of gold and stuff. Well, those are hydrothermal features. Those are actually forming in like deep ocean vents and things like that. You don't have deep ocean vents on asteroids. You never had deep ocean vents on asteroids. There's no prospect of having nuggets or anything concentrated like that. And they're not found in meteorites. You know, if they're found in meteorites, I'd say, well, you know, so much for the theory. But they're not found in meteorites. You don't find that stuff in meteorites. When they say there's platinum in asteroids, what they mean is there's metal, iron, nickel, meteorites that fall that have got 5% platinum or something. So you'd have to find one of those things and then melt it somehow and extract the platinum, or you'd have to bring the whole thing back to an Earth orbit. Both of those are going to be really expensive. So it's not going to be platinum. And yes, a lot of asteroids have diamonds. Unfortunately, they're about a nanogram, which means, you know, you couldn't see them. Some of them have a little bit of gold, but it's the same thing. You have to smelt it out somehow. And so these precious metals, they're just not going to cut it. And I think the lesson there is the industry won't be built by bringing stuff back to Earth. That may come later, but that's not what's going to build the industry. It's going to have to be used in space. All right. And I think most people who worry about this now think that the first thing we're going to mine is water. So in a way, it's more like petroleum extraction than mining, but you know, that's the terminology people use. So why would you want to mine water? Well, because it's there, because it's useful. We need water to drink. On the space station, the ISS, they have about an 85% efficiency of water. And so they need a couple of tons a year of water to keep that thing going. A 2.5-year mission for 4 men or women to go to the moons of Mars, Phobos, and then come back. They're going to need something like 4 or 5 tons of water for everything. Because they don't just use it for drinking, they use it for breathing. You make oxygen out of it. And the 2 bottom ones are really sort of the wild cards here. Because if you have to bring it from Earth, it's non-efficient to have radiation shielding. They're going to go without radiation shielding because it's just too expensive to bring the tons of stuff that you would need from Earth just for radiation shielding. But they actually need radiation shielding. The galactic cosmic rays on a round trip to Mars are supposed to significantly increase your cancer risk. And that's something they worry about a lot. There's arguments about, you know, well, how much should they worry about it? Maybe the astronauts would volunteer anyway, which they probably would. But the fact is, you know, the doctors don't like this. And they're pretty worried about the fact that you probably can't take 2 trips to Mars without a risk of getting cancer being fairly high. That's with no radiation shielding. And then there's agriculture. I don't know if you're following the news today, or yesterday and today, but they're just about, I think tomorrow morning, they're going to do the first harvest on the space station. They've been growing lettuce, and they're going to harvest this lettuce and they're going to eat it. Well, actually, they've had harvest before, but they didn't eat it. They brought it back to Earth. But this time, they're actually going to eat it. They're going to expand their cuisine by having fresh lettuce. And if you ever talk to an astronaut, I mean, I talked to an astronaut about this, when they send up one of those Progress resupply spacecraft, they always make sure to have some fresh fruit right on top. You know, it's full of cargo and this and that and the other. But they always make sure they have some fresh fruit right on top, because you know the fruit's only like 2 days old when it gets up to the space station. So they say they open the door, the hatch, and there's like an orange there, an apple, and the smell of that is just so intense because they haven't had anything to smell for months that it's just like wow, an orange. So if they can grow stuff up there, they should be growing stuff up there, and that takes water. All right. And in fact, even the lettuce they're growing is basically hydroponic lettuce. And the thing that sort of interests me about this is, if you look at the cost of sending a kilogram of anything to Phobos, it's going to be in the several $1 million range. So if you could say we can bring you water from an asteroid at the cost of, say, $1 million a kilogram, it's actually cheaper. And so that to me is a sort of a good market little thing where you have the customer doesn't know they need this, they're going to do it yet. We're just starting to talk to them, but the customer should realize, oh, this makes sense for us. It's a way of getting water that we otherwise would have to pay too much for or couldn't get at all, and yet it would help fund the development of asteroid mining. Because you need something that's around $1 million a kilogram to have this make sense. If you have $1 million a kilogram, it makes sense. There's a few things you might get from the moon that's at that level, but really from the asteroids, it's got to be stuff like people going to Mars. I mean, they don't have to be going to Mars. It could be high lunar orbit, which is what they're going to do first. Pretty similar. Okay. Then there's planetary defense. I'm not going to say too much about this here, but the fact is that the needs of asteroid mining and the needs of planetary defense right now are pretty similar. Because in both cases, we need to know what kind of asteroids there are, what are they like, are they solid bodies, or are they big rubble piles, and that sort of stuff. So at the beginning, I think the technology development is going to come from planetary defense as well as asteroid mining. And I'll show you pretty pictures and sort of a cool mission plan for that later on. And so there's these three companies. There's Planetary Resources, which is out of California. There's Deep Space Industries, which is kind of sort of out of California, but the president and founder, David Dunn, is actually in McLean. He lives in McLean. So he comes to a lot of DC space events. And then there's my company, Asteroid Initiatives, which is right here in Virginia. And it's kind of funny, when Planetary Resources started out, they were talking about platinum. Oh, in fact, you still hear this stuff. Such and such an asteroid is worth $1 trillion, or $5 trillion, or $100 trillion, whatever, some large number. And the trouble is, like I said, it's hard to see how it'd be worth getting it and bringing it back. And so if you can't afford them, if you can't make money on it, you can't say it's worth that, in my opinion. It's like saying such and such is worth $1 trillion, but you can't actually get it. So it's not really worth $1 trillion. But deep space, the scientific brain behind Deep Space Industries is Professor John Lewis, who was at MIT. I actually took a class from him when I was at MIT. Very interesting guy, and moved to University of Arizona and spent most of his career there. And he all along was saying water, and he was right. And recently, Planetary Resources, Chris Lewicki was at JPL and is now up in Seattle, I think, or Redmond, somewhere up there. He's agreed, yeah, it's going to be water. So everybody's sort of agreeing, yes, it's going to be water and associated things, maybe a little hydrocarbons. And they provided some figures here, so I'll point that out. So the realm of the small bodies here. As of January 1st, there were 664,033 asteroids that had some level of believability. And there's there's ones that have been seen once, but they're not here. These are ones that have something like an orbit. However, most of these are actually lost in the sense that you couldn't say today, here's where you point your telescope where you can see them, right? And that's the definition of lost. Now, that doesn't mean they won't be found again. Typically, these things are small. They do an opposition with the Earth. You see them in opposition with their opposite the Sun. And so, you know, somebody, you know, in opposition today or in a year or 10 years, 5 years, whatever, says, oh, I found this asteroid, it's a new one. And then somebody does the math and says, no, it has the exact same orbit as this other guy, it's the same body. So that happens all the time. But I think here's an appropriate point to say how important amateurs are to this effort. Yes, there's a lot of money going into this discovery and monitoring of asteroids, but really amateurs provide the underpinning for much of what I'm going to talk about tonight. There's just too many, 600,000 of these guys, for the professionals to look at every one all the time. Many of them are lost, and so they'll be picked up by people who are not looking for any particular asteroid, but maybe just taking a picture of a deep sky object or something. So what do the amateurs do? They actually do three things. They do astrometry. Now, it is the case that if you want to discover a new asteroid today, you probably should have a telescope that can get down to at least magnitude 20. So that's a fairly large one. Magnitude 22 would be better. Because they do these wide sky surveys that take pictures of the whole sky every night, and they tend to be the ones that discover the new asteroids that are in opposition. However, there are lots of asteroids that are, you know, that need more observations, and the amateurs provide most of those observations. Occasionally you get the guys getting out the big guns or something that's going to have a spaceship go by or something. By the big guns, I mean the big telescopes, you know, like Hubble or something like that. But mostly that's amateurs. And amateurs provide a lot of the rotational information. Because the survey telescopes will take a picture. Typically they take two pictures. They take one now, and they take one in half an hour or so. Just so they can say it's not a cosmic ray hit or some other, you know, bird or something. It's an actual body that's moved a little bit until it's not a star. But to get a rotation rate, you need to take multiple images, ideally in a night or over a few nights while it's bright. And a lot of these guys rotate very quickly, half an hour, 15 minutes, 10 minutes, 5 minutes. The fastest rotating one is about 30 seconds. So if you got a big enough telescope, it doesn't take a lot of observing to get a rotation period. It just takes them multiple images. So that's another thing the amateurs do. And then there's the International Occultation Timing Association, the IOTA. And how do you find it? I mean, basically all the asteroids except for the few biggest ones like Ceres are not resolved by telescopes. They're always going to be points of light. So how do you find out something about how big it is, whether it's, you know, a football shaped or a sphere or whatever, without actually sending a spacecraft there? Well, one of the best ways is through occultation timings. And what that means is there's a star, you predict that the asteroid is going to occult, pass in front of the star. Now, the star might be 6th magnitude, so it's bright, so you don't need a big telescope for this. You know, what you need is good timing. You need the ability to have like a photometer or a CCD that's taking lots of images, and also some sort of, you know, 20 years ago this was a lot tougher because, you know, you'd have to be listening to WWV or something to get timing. Nowadays with GPS, you can just have the equipment that says, okay, here's the time to a millisecond or better. And but what the amateurs do is they give you a spread. And so the amateurs can get there in lots of different locations and say, oh, I saw the star blink out. And then by collating all of those timing things, they actually can get a map of what the asteroid looks like in cross-section at that instant of time. So that's really important and something that I think a lot of amateurs could contribute to. Asteroids get perturbed by other asteroids, they get perturbed by things hitting them like meteors or smaller asteroids, they get perturbed by solar radiation pressure, they get perturbed a little bit by the orbits of the Earth, Mars, and so on. And they wander around here until they fall into one of these gaps. And then it's kind of like, having your hole, like maybe say you're at a star party and there's a hole in the ground. You're walking around, all of a sudden you fall in the hole, and wham, you're not in the same trajectory you were before. And so, like I said, this is a way of getting stuff out of the asteroid belt, closer to where we are. It can also eject into the system entirely, it can have fallen into the sun and so forth, but we care about the stuff that comes close to us. So the life cycle of a near-Earth object, or a near-Mars object, is it was in the main belt at some point. It got perturbed enough by whatever cause that it got in one of these Jupiter resonances. Then quickly, over the time period, maybe 1,000 years, which is really quickly, you think of something that's been there 4.5 billion years, its eccentricity gets high enough that the perihelion comes down here to the Earth, Mars, even Venus maybe, and then it interacts with the Earth, Mars, and Venus, and that changes its semi-major axis down to something low. So it's a sort of two-step process. You're coming down, and it's effectively random gravity assists. You know, we put a lot of effort into doing gravity assists where you plan it very accurately. Well, you know, so like if you have enough monkeys typing, you're going to get Shakespeare. If you have enough asteroids rotating around, you're going to get gravity assists. And that's going to lower the apoapse from the belt down. And a lot of these asteroids, though, still have the apoapse up in the belt. So even though the semi-major axis has been lowered, the apoapse is still out there. And that's very common for near-Earth asteroids. And that means when they come by the Earth, they're not coming slowly. So they're not such good candidates for asteroid mining. They're coming by 10 kilometers a second or so, you know, and that takes energy, and energy is money. And notice, all we've been doing is really simple stuff that you have for every asteroid. What's its orbit size? What's its actual size? You know, its absolute magnitude. That sort of stuff. You know, most of these asteroids, we don't know anything about them really. We don't know their composition or anything. We just have these sort of gross things, but you can find out a lot from them. And so if you, everything in space tends to be some sort of power law. You know, there's a few big things and lots of little things. There's one big Jupiter, and then the rest of the solar system is about a third or a quarter of the mass of Jupiter. And so there's a power law in solar system stuff. There's power laws in the asteroid, and that's thought to be typically because of collisions. You know, if you have a few big things and they start hitting each other, then you start to get lots of fragments, and you get a power law there. You get lots of little fragments and fewer big ones and so on. And so the typical idea is when you see these surveys, these are cumulative now, this bump here is thought to be related to something primordial. A lot of discussion about that. But you come up here and at some point, you stop getting smaller bodies. And it happens to be that that's just about the magnitude, the size, where the surveys become inefficient because you're not seeing them as many as you are, as you should. So the whole thing hangs together fairly nicely. And that says that, you know, the near-Earth bodies are probably complete down to a kilometer maybe, and the main belt guys are probably complete down to 2 or 3 kilometers. And that still means there's lots of smaller bodies. Now, you know, trees don't go to the sky, these things don't go up to infinity, but the notion that there might be 1 million near-Earth objects, mostly at the 100-meter level, is not that unrealistic. In fact, that's kind of what we expect. Now, fortunately, from a planetary defense standpoint, this is about where the civilization killers are kind of in here. So we think we know where almost all of the civilization killer-sized bodies that might come near the Earth are. There might be a few that have escaped, but we kind of have that nailed down. Chelyabinsk is way over here somewhere. Chelyabinsk is about right here. So with Chelyabinsk, we're, you know, we're getting 1 per 1,000 maybe. So our ability to predict the next Chelyabinsk, you know, that kind of, you know, large meteor of 30 meters or 50 meters or whatever, exploding over a city and maybe hurting people, is basically nil. You know, we can predict one case in 1,000. And I thought I was sort of encouraged to do technical things. This is something I find fascinating. This is the rotation radius thing, curve here. This is every asteroid that has a rotation rate. And that's 6,000 or so out of this 600,000. So that's about 1%. So clearly getting more rotation rates is a good thing because you can find out a lot from the rotation rate. So what do you see here? We see that for sizes between, these are radii, about 100 meters, say, and maybe 10 kilometers, there's a very sharp line here, and I can show blow-ups. quite sharp. You don't see bodies with periods faster than about 2.2 hours. And why is that? Well, if you imagine saying, what's the speed at which the body will start losing stuff at the equator? You get an equation like this is for a sphere. The rotational frequency squared is equal, this is really just Kepler's law. You're saying that the stuff is in orbit at the equator. You know, g times the mass divided by r cubed. And so since the mass depends on r cubed too, the radius drops out and you just get this g times the density, rho, times this 4/3 pi. And so the 2.2 hours translates to a 2.3 grams per cubic centimeter density. And that's actually very, very nice number for asteroids. That fits right sort of where people would expect. So people really do think that this is a sign of the rotational disruption of asteroids, that if they spun faster than this, oh yes, there's one guy here, and there's another one that was discovered last week that's sitting up there. So there's a few oddballs. These guys here, though, are almost all faster than that 2.2 hour limit. And they're small bodies. And there's a lot of discussion about, well, what does that mean? Somehow they're stuck together. Either they're like boulders that are one monolithic thing, and you know that seems attractive, but it's hard to see how you have a boulder of a small thing, because these size are not primordial, almost certainly they're blasted off something else. So how do you have a boulder that's blasted off and yet it's in one piece? Or maybe there's van der Waals forces or some other force that's going on. But you have this really interesting thing here where you have the, below about 100 meter size, you have fast rotators. And now if you actually want to mine an asteroid, this is also important, because this says, you just say pick a random, 50 meter, 75 meter asteroid, it's probably going to be rotating pretty fast. In fact, if you just say they're spherical, and you don't really know the shape, if you just say they're spherical, you see a lot of these guys have surface accelerations at the equators outwards as high as a few tenths of a meter per second squared. And that's kind of worrisome if you're thinking about doing stuff there. I mean, instead of saying, I drop this and it falls to the surface, it's like I drop it and it goes out to infinity. Let's look at a few of these guys and, close up. I mean, one advantage of working with asteroids as opposed to galaxies or something is that you can actually go and look at them. You can send spacecraft there. We can't send spacecraft to M31, but we can send spacecraft to an asteroid. 3 of them have had fairly slow flybys, and then a bunch have had fast flybys. Eros and Nikawa have had spacecraft come and stay a while. So there's an interesting thing that comes out of this too. This is Ida. This was passed by with Galileo on its way to Jupiter. And this is sort of what people expected. This is the first asteroid to have a flyby. Ida also has a moon that's been named Dactyl. It's maybe 2-3 kilometers across. This is 60 kilometers here, so this is a pretty big thing. And when this picture came out, this is what everybody expected, kind of. It's a small body, it's been around forever, it's got lots of craters. It's just like the moon, or Callisto, or something, or Phobos, It's got lots of craters. So, big deal. It's an old body, nothing's happening there. It's the equivalent of, the dead zone. But now, this is Itokawa. This is 500 meters. And yes, it looks like 2 potatoes that have been smushed together, so maybe it was a contact binary, maybe not. But if you look at this, you see a couple of interesting things. You don't see any craters. And the gravity here is really low. The gravity here is like, the escape velocity is a millimeter per second, or something like that. The gravitational force is 10⁻⁴ meters per second squared, something like that. 10⁻⁵. I may have this here. Where are the craters? Why is it when they hit, you don't have all kinds of craters? Now, there's a theory that's been derived that, well, maybe the crater hits, a meteorite hits, and the thing shakes like a bowl of jelly, and then that smooths out any craters, and so they're lost. Well, okay, but then it's hard to see, given the really low gravity, why the thing just doesn't fall apart then. If it's shaking, why you just pieces go off in all directions, and there you go, you don't have an asteroid anymore.
And then you have things like, well, this is another picture of Itokawa. You have the ponds or the seas here. And they've been seen on every one we look at, every small asteroid we look at up close. And you have like the round shape here. Now again, this is a body that looks like a Roboplot. It has very, very low gravity. How does it keep this nice round shape here? If the thing is shaking and that's why the craters are being removed, why doesn't it just mush together into some blob? You know, how does it maintain its shape some ways and not others? I'm sure that there's answers to all of this stuff. We don't know what they are. So there's some mysteries here about these small guys. What is going on here with this fine stuff? Why is that material in certain locations and not in other locations? You know, what holds it together? In this particular body, Itokawa, the Hayabusa spacecraft, got really up close to this, the Muses C, as they call it, which is actually a joke in Japanese. And it seems to be little tiny pebbles about the size of a pea, or maybe an English pea, you know, something like that. Some fraction of a centimeter, probably a little over a millimeter. Similar ponds, as they call it on Eros, the near spacecraft got close to them, and it never resolved them, so they're smaller than a millimeter. So what keeps this stuff together? Why doesn't it just fly off into space? How is it flown here? These are all things we don't really understand. They're theories, but we don't really understand what's going on. And so there's also radar. And radar is kind of interesting. If you look at the raw radar pictures which come out, there was one of a binary that came out Monday, I guess. A lot of times they're hard to interpret. You know, here's an asteroid, 1999 KW4. This is where they found it has a moon. Well, yes, clearly it looks like there's something here and there's something here. But what does it look like? What's it going on? You gotta do computer modeling. Unfortunately, people do that. And this is what it really looks like here. So you have something that's roughly spherical. It's got this is the equator, this is the pole, north pole, say, the south pole. This is the equator here. Notice it has a sort of a ridge along the equator. And then you have this thing that looks kind of sort of like a cigar or a small potato that's orbiting it. And this is in a rotationally locked orbit. So it's always, the long axis is always pointing at the main body. This is rotating around. I have a video of this, you should see maybe. So the theory is here, this thing is rotationally, and this thing is rotating almost at that 2.2 hour limit. It's like 2.3 hours. So it's almost rotationally unbound. And in fact, the prediction of the acceleration right here on this ridge is 0. So maybe it's a little positive, maybe it's a little negative, but it's 0 within the numerical, the experimental uncertainties. So the theory is stuff flows down to here, and then it gets accelerated, the rotation gets accelerated maybe, material falls off, it's then in orbit, it doesn't go to infinity, it's just in orbit, and there's this moon here that's basically made by slurping up all the stuff that falls off. So the moon might have been a primordial piece, or they're all along, or it might just, some people think only about 10% of these bodies, 15% maybe, have moons. Some people think the moons fall apart and then recombine. So depending on when you come and when you look at it, sometimes it'll have a moon, sometimes it's not. They're really effervescent things, unlike our moon, which has been around forever. So here's some upcoming missions I want to talk about. There's a number of interesting upcoming missions. There's Hayabusa 2, which is on its way right now. There's OSIRIS-REx, which is going to launch next year. That's a really cool mission because these are both sample return missions. There's nothing like having a sample return. There's the Asteroid Redirect mission, which is something I'm involved with. There's the Asteroid Impact and Assessment mission, which is actually 2 missions, AIM and DART. And I want to look at ARM and AIDA, or AIDA. Let you guys know what's going on here. So ARM is the Asteroid Redirect mission. And this is actually a fairly complicated mission, which is really intended to, the story I've heard is that Buzz Aldrin, when Obama was elected president, when he was inaugurated, soon after he went into power, Buzz Aldrin went to see him.
and said, we need to send people to asteroids. It's a good step along the way to Mars, and it's, you know, you can have boots on the ground and all like that. And Obama said, oh, that sounds like a good idea, and make it so, kind of. And then they started running the numbers, and they found that for the asteroids they thought they could get to, mission durations were long enough that the radiation was actually pretty bad, and it would violate the NASA guidelines for radiation, which were actually derived from the Nuclear Regulatory Commission guides for radiation for nuclear workers. So the asteroids are basically viewed as nuclear workers. And just like nuclear workers, they all have a lifetime exposure limit. So every asteroid can tell you, every astronaut can tell you what's my life and how many rims I've got. So the mission was changed slightly to have a spacecraft go and grab something from an asteroid and bring it back to a high lunar orbit so that the astronauts could go up there and look at it. Now, this is not, some people thought, oh, this is just make work for astronauts, but it's not actually. If you're going to have a mission to Phobos, and a mission to Phobos is pretty clear, is going to be the first stage of landing people on Mars. The first thing you do is you orbit Mars, and then you land on Mars. And we're actually building right now the technology to get people to orbit Mars. All of that's in the works right now. The lander hasn't been approved yet, but to get there is actually pretty similar to just orbiting the moon, right? If you can do the one, you can do the other, more or less. The energies involved are pretty similar. The time is a lot longer, so you need a HAB or something like that. And if you pay attention, you might notice that Charles Bolton has been talking to ESA about deep space habitats. And pretty clearly, I think some sort of deal, I don't know anything inside, you know, so I'm just observing on the outside here, but I think there's some sort of deal that's going to come out where ESA is going to provide a habitat for this long duration mission, and, you know, it'll be ESA, just like the space station, it'll be a combination of ESA and American astronauts. So the mission is, you go to an asteroid, you find a boulder, 10 tons maybe, it could be up to 40 tons. You bring it back to a distant retrograde lunar orbit, and then there's a defense test too, and then you have astronauts look at it. So the astronauts going out to look at it is very much like astronauts going to Phobos, except they have an abort capability. If something goes wrong, they can be back on Earth in 36 hours. And the mission, the manned spacecraft people really want that capability because they don't want to be in a situation where they, you know, the first flight is something where you're going, and if something goes wrong, you can't come back. You know, that seems like not a good idea. So basically, the arm would involve this fairly large spacecraft. It's solar electric propulsion, so here are the solar panels. It's identified a boulder in this thing. Boulders are certainly there. I don't know if you remember the picture of Itokawa. It had lots of boulders on it. Every one we looked at seems to have boulders in this size range. One question is, are they really boulders or are they dirt clods? If you pick it up, will things go and you get a whole bunch of dust, or is it something, you know, intact? I mean, it doesn't have to be one piece necessarily, but it needs to be something you can actually pick up in a gentle fashion. Remember, these are small bodies. Gravitational accelerations are really small, so, you know, a millimeter per second is a sort of fast motion here. And so here's an image. You see that these xenon solar electric propulsions are in fact blue. They have a blue exhaust. It glows blue. And it's got this boulder here, and it's going to bring it back to Earth. And it does this gravity tractor where it's going to do this pseudo-orbit. Now, it's not a real orbit because the gravity is too low. It's using its thrusters to be in an orbit here. And the idea is not on center, it's off center. It orbits this way, and that pulls the spacecraft that way. And if you sit here for 60 days or so, the velocity change of the spacecraft is a few millimeters per second, which you should be able to detect. And so this is a planetary defense test here to see, you know, could you use this deflection here? And in fact, you know, the thing about the gravity tractor is the spacecraft never touches the body. You could probably land the spacecraft on an asteroid and have the rockets go the other way and then push it, and it wouldn't fall apart. I think that's a fairly good bet. But the trouble is that you land the spacecraft on the asteroid, and that, you know, what if you sink into it? What if it, fissures in half where you are, or something like that. The spacecraft, the guys that run these spacecraft don't like the notion of touching things. They'd much rather have a planetary defense thing where you're not touching it. And that's really why they like the gravity tractor. And then eventually it's brought back to Earth, where the astronauts can come look at it. This is actually the constellation thing here. It's in this distant retrograde lunar orbit. See, that's supposed to be the Earth over there, that's the moon. These are orbits. Probably a lot of you here have heard of Lagrange points. A lot of people think, well, the Lagrange points are stable things where you can stick things. Well, actually for the Earth-Moon space, the solar perturbation is so big, Lagrange points aren't really that stable. You could not count on, you could not leave something at a Lagrange point and say, I'm going to come back in 20 years and it's going to be there. The distant retrograde lunar orbit should probably come back in 200 years and it would be there. They're very stable. And the reason they're stable is, the difference is they're going against the orbital rotation. And so instead of being more or less in phase with the Earth, where the Earth's, they're against the Earth's, perturbation, against the solar perturbation. Everything happens fast, and so it doesn't tend to build up as much. But if you're putting stuff that's massive out somewhere, the DRO is a good place to put it, because you always have this worry, well, what if, the rocket breaks or something, so I can't use these rockets anymore, I have to develop new rockets or whatever, or there's a hideous earthquake at Cape Canaveral, and the Kennedy Space Center is destroyed, so it takes 20 years to build it back, or something like that. What if this is a long interrupt between, that I have no control over, between when I put something there and when I can go do stuff with it? You'd rather not have it fall out of the sky and become a problem. And the DROs can do that, and so I think you're going to see a lot of use of them going forward. And in fact, one of the things they're talking about that I regard as almost a certainty is some sort of crude habitat in the DRO, so you have astronauts up there all the time. And of course, if you were going to do, say, platinum group mining, that you were going to process material, that's where you bring it to, is the DRO. You almost certainly bring stuff. So I think that's not 10 years from now, but 30, 40 years from now, but I think that will happen too. AIDA. I like the opera, so I call it AIDA. Although the East people tend to call it AIDA. I don't know. It's a very complicated mission that nobody's heard about. The idea is there's this asteroid, DDead of Us, which is a binary. It's very similar to the KW4 with the little cigar-shaped moon and the more or less spherical thing with a ridge. It's about 2/3 the size. The primary is about 800 meters. It's a pretty good sphere. The secondary is about 170 meters long. So the idea is that AIM would provide a spacecraft that would run into the Didymos and instrument it, measure it, figure out what's going on, make good maps and all like that. And then on October 1st, 2022, to within 2 or 3 days, there's a little slot there, but not much, the DART spacecraft. And DART is actually going to be built from leftover pieces of New Horizons. It's going to use the spare New Horizons engineering camera or something like that. It's literally going to use parts that were built for New Horizons engineering tests, because NASA figures, well, by 2020, when this thing has to launch, New Horizons will have done its thing and we won't need a camera for an engineering test after that point. So DART's going to be made on the cheap, and it's going to hit the moon at 6.25 kilometers a second. And that's pretty fast by human standards. A fast artillery piece is maybe 1 kilometer a second. So this is fast enough that basically the thing will vaporize instantly and then do, well, who knows what. But this is called a kinetic impactor asteroid deflection. And this is what you would do if you had something that was coming that you didn't find in advance, that you really wanted to take care of quickly. You don't have time to have something sitting there and moving it about a millimeter per second over months or whatever. You want to get it out of the way right fast. And the reason they're using this moon, well, there's 2 reasons. A, this is an asteroid that has a moon. So if you hit the asteroid, the moon that is, and you move it in its orbit, it's tied to the main body. And so you can say, well, we changed its orbital period or something like that. Because whenever you have an asteroid that's just out there and it has some perturbation, the observations are perfect, and you know, it's frequently hard to say, well, what's really going on with this? They have a much better handle on things if it's in an orbit. And the other reason is this is actually a transiting binary. In fact, in April of this year, it transited. And what that means is once or twice per orbit, it all lines up so that the moon gets in front of the asteroid and the asteroid gets in front of the moon, and so it's a transiting binary. And that's another thing that amateurs can help with. There are not many, there's, like I said, about 10% of the asteroids that have enough data seem to be binary. And so that's the conventional wisdom, is that probably 10% of the mid-sized ones are binary. But not many of them are transiting. And transiting gives you a lot of information. And in particular, that means that if you move the moon, you can wait from the transits in April this year to the transits in 2024, I think they are, and have a really good indication of what happened. Even if the AIM spacecraft didn't work. So even if the ESA one blows up in the pad or something, never gets there, you don't need it. You can get what you need to do. The essential part, did you move the moon or not, from ground-based stuff, and from amateur ground-based stuff. So ESA's put a lot of effort into this, and we're actually part of a proposal on this. It's a phase 8 proposal. We'll see how far it goes. Here you have the main body with its equatorial bulge here, a ridge. Here's the secondary. Here's the AIM spacecraft. It's going to deploy CubeSats. We're hoping to deploy FlatSats, which are really small spacecraft. 80 by, the footprint is 80 by 35 by 5 millimeters. Nowadays, you can make everything miniature almost. They can have cameras on it, they can have accelerometers, they can have magnetometers. Put them on the moon. So here's an artist's rendition of this. You have the CubeSat. It's putting out these little credit card sized things on this moon. At the time of the impact, the Earth will be 10.5 million kilometers away. And that means the Earth will be about a fifth the size of the full moon. So you should, if you were there, human, you should clearly be able to see, yes, that's a moon, that's a body, it's a sphere, it's got some sort of structure on it. You might be able to see the biggest continents. So this is not that unrealistic, which we really don't these things look like. And then the DART spacecraft comes. The main spacecraft backs away 100 kilometers. It's out of the way here. The CubeSats, however, are just sitting on the surface. And the notion is, you put down 50 maybe, and so if half of them get destroyed, well, we still have 25, something like that. Here it comes, it hits, and this is an artist's rendition of what might happen. In this case, the idea is it's penetrated deep into the body, and basically what tends to happen with impacts at high velocities, hypervelocity impacts, is the thing has a lot of kinetic energy, so it just hits. It creates a shock wave, it vaporizes stuff, and it just keeps going until it reaches a point where the losses start slowing it down, and then it slows down really fast. And so it dumps all of its material into the body. And that's, for example, why, like if you've been out to the Barringer Media Crater out in Arizona, and if you have a chance, do that. It's really phenomenal. The 100-meter body comes in, hits the surface, drills down into the surface, and then dumps all its kinetic energy out about 200 meters underneath, which is effectively an explosion, and then that lifts the stuff out, plops it over, and that's how you have this crater that has the material that was below is now on top of what was the old surface. That's how craters work. I mean, if you look at a lunar crater or whatever, that's what they are. The stuff that was here was lifted and plopped up because the kinetic energy was released down in the body. Well, this is like, kind of like it's driven a tunnel and then it's pushing out the tunnel. Maybe, maybe not. We don't really know. We don't really know what's going to happen when this happens, and that's kind of cool. You know, it may disrupt the body entirely. It may just send it to a gazillion pieces. You know, it may have a jet coming out the other side. It's only 50 meters across, you know. Hopefully we'll see. And then everything, instruments and all like that, you can see how having even simple instruments distributed along here
to provide you really valuable information. One of the things we hope to capture is, the theory that this thing will then shake like a bowl of jelly. Well, if you run the numbers, it's supposed to shake at about a meter per second for 8 hours or so. That's a, accelerometer. The accelerometers in your cell phone would have no trouble picking that up. Right? Your cell phone has accelerometers in it. It has probably a gyroscope in it. It has no trouble picking up accelerations at that level. I mean, that's how it knows, when you pick it up, after all. That's how it knows how it's oriented and so on. So this is from Planetary Resources. This is their idea of what you would do to capture an asteroid. You'd have to find one that's the right size, and you have to, you have this tent-like thing that sort of globs it up. And this was actually the original idea for AIM. And the trouble with this is, these bodies are, the bodies of a size that you can do this are 5 meters maybe at the most. Well, it's very hard to see 5-meter bodies. You only see them when they come close to the Earth. And what you typically find is, some amateur finds it or something like that. It's visible for 2 days, and then it's gone, off far from the Earth again, and we won't see it for 50 years. And that makes it really hard to plan a mission, because you can't keep one of these things as a practical matter. You just can't keep one on the pad ready to go like some ICBM. So, here's an asteroid coming by, push the button and send it. No, you need to plan it in advance. And you just don't have many candidates like this. In 100 years you probably will, because the stuff we're discovering now will start coming back. But, that's a long time to wait. And then I think what we're trying to do is, we're trying to do 2 things. One, we're trying to propose to NASA that NASA should pay for resources delivered to astronauts. And we have to figure out what that is and how that will be, and get a space Act treatment in place and all like that. The other is prospect asteroids. And I think the AIM mission would really set up how to do that. Because I think the way to do that is with these little tiny spacecraft. Because, let's say you wanted to have an asteroid prospector, and actually all 3 companies want to do that. What would an asteroid prospector be? Will it be something, maybe it's a CubeSat, which means it's not much bigger than my briefcase here. Maybe it's a little bigger than that. But probably something in the order of 50 to 100 kilometers at most. Kilograms, rather, 50 to 100 kilograms at most. Something you could pick up, without risking hurting it too bad. Maybe with a solar sail as propulsion, maybe an electric sail, maybe solar electric, which means you've got big solar panels, something like that, because you need, typically if you do the math, which we've actually done test missions, you can hop from one asteroid to another. It's going to take you a few kilometers a second. So if you're going to look at 10 of them, you need the ability to change your velocity about maybe say 20 kilometers a second. It's a lot. You're going to need something like a solar sail, or an electric sail, or a solar electric propulsion to do that. You're not likely to do that with chemical, because it'd be too expensive. Well, all of that says when you get to the asteroid, you're going to have some big solar panels or something. You're probably not going to want to land your little spacecraft on the asteroid. You don't want to touch it again. So you're going to need something like these little prospector chips to go down to the surface of the asteroid and get your information there. And so-called NIMS devices, we can look at chemical stuff and all like that. And not, solar sail is a great example. Solar sails are cheap. They're using solar radiation pressure. The trouble is you can't turn them off. You cannot turn a solar sail off. The solar sail prospector will never be able to really linger very long. Yeah, it might be able to tack around the asteroid once or something like that. But basically, it's going to come, it's going to say hi and take some pictures and do whatever it's going to do, and then it's going to move on because it has to. And for goodness sake, you sure don't want to get the asteroid to touch the sail, because then you don't have a sail anymore, it will collapse. And so you're going to need some sort of little probes to send down to the surface of the asteroid so you get the kind of information that we're interested in. For example, just that water. One advantage of an electric sail has not been tested as much. In an electric sail, you are reflecting the solar wind. If the solar sail is about a factor of, I think, 400 in terms of flux density, so you need 400 times the area, or what would that be, 20 times the size, and so if a 10-meter solar sail would work,
You need a 200-meter electric sail, but it's wires instead of a sheet. This is a sheet. The electric sail is wires. And if you turn off the current, the electric sail stops. And so it's not generating thrust. You cannot turn off the solar sail. Solar sails have little wrinkles in them. And so even if you imagine this being the solar sail, you're reflecting, say the sun's back there, you're reflecting from the sun. Cool, you say, well, I'll just turn it this way so it's edge on. No, it's got little wrinkles in it. And so, in fact, when you've done these things, they don't think they can get below about 5% of the thrust. Well, 5% of the thrust is still too big for, to stop at an asteroid. It's just going to go by. And electric sail has some advantages. I don't know, you know, really the question is what's the most practical here? I think we don't quite know that. So in conclusion, I think as a business proposition, this is a pretty risky thing. However, I think it's becoming clearer rapidly, actually. In the last year or so, it's become a lot clearer what we can do and what we can do that could make some money. And clearly, this is going to be, just like the airlines, just like many technologies, this is going to require government assistance or friendly government, you know. The government's got to be friendly, at least, for this to work. Because the government is going to be the logical customer to begin with. You know, now, of course, if people start sending colonies to Mars or something, well, they could be customers too. But I personally don't see that happening in the very near future. I think we're going to have government stuff going to Mars faster. One level, I don't care. They're going to need water. Now, of course, once you land on Mars, you can get water from Mars. But even if you land on Mars, you're still going to need water to get to Mars. And if you send anybody back, they're going to need water coming back. And you should only be lifting water from Mars because, you know, that's very expensive. I think that these, you know, starting to develop and actually deploy these tiny little spacecraft is going to be really essential here. I think that's the way to do this, is to have, you know, have everything as small and as cheap as possible. So in fact, that's it.